Hi everyone. I'll share my screen. Hi, is the screen visible? Okay, great. So welcome to week 6 of our classical mechanics course. Hope you had fun learning this week and also happy Teachers Day. So we'll start with recap as our custom is. The recap of week 6. Before that, we had seen earlier that conic sections are literally sections of cones, right? If you cut it horizontally, you have epsilon is equal to 0, that is circle. If you cut it at some angle, you have epsilon between 0 to 1, and that is your ellipse. If you cut it exactly at the angle of cone, you have parabola, for which our eccentricity is 1, and if it is higher than that, then it is hyperbola. And at first it might seem like just an exercise in mathematics. Why the hell we are doing it in classical mechanics course? But as it turns out, when you solve Kepler's problem, what you get is an equation that looks something like this: R is equal to some number rho divided by 1 plus epsilon cos theta, and that is exactly those things. Depending upon value of this parameter epsilon, you can have all kinds of conic sections as your orbits of planets, right? So, and that depends on your energy and angular momentum. So that's what we started with Kepler's problem, which means we are taking u of r as minus k over r, inversely proportional. So this is inverse square law. If you take force, it's derivative of this. So there is that, right? And so when you solve it, at the end you get an equation for r that looks like L square by k mu divided by 1 plus epsilon cos theta, right? In general, it is theta minus theta naught, where theta naught is the angle where the perihelion occurs. But we can rotate our coordinate axis such that theta is equals to 0 is that direction, or the x-axis, right? So we generally ignore that theta naught. It's the setting of the coordinate axis, and we found that epsilon is given by 1 plus 2e L square by mu k square. All of these numbers are constant for a given problem. Angular momentum is conserved. Mu is your reduced mass. K is just Gmm, and E is the energy that you start with, right? So immediately you can see that depending upon value of E, you have the bifurcations in your epsilon. If E is less than 0, then epsilon would also be less than 0, right? At E is equal to E minimum, your epsilon just becomes 0, and that E minimum would be, you can calculate, minus 1 by 2 mu k square over L square, right? And that is your circle. And for the circle, the radius would be given by L square over K mu. Okay, so these two are for circles. When e is less than 0, you have ellipse. When energy is just 0, it means, oh, sorry, this belongs to 0 to 1. When energy is just 0, it means your epsilon is 1, right? From this one, it means a parabola. So parabola is a very special kind of orbit where energy is exactly equal to 0. Change it a little bit, it either goes to ellipse if it reduces, or it goes to hyperbola. So if it is more than 0, then epsilon is greater than 1, and that is your hyperbola. Okay. In terms of energy, we can write this as U effective versus R, and it looks something like this. So this is where your circle is, right? The minimum energy. Then this is your ellipse. This is your parabola, and this would be hyperbola. Okay. Then we saw that for a particular ellipse, we can write R as L square, same formula, but epsilon is between 0 and 1. So minimum would be when cos theta is maximum. That would be plus 1. So when cos theta is 1, you have this. This is called perihelion, right? And that corresponds to theta is equal to 0. So if theta is equal to 0, which means on x-axis, you have your planet the closest. And this is your perihelion. Because if this is your sun is Helios. It's closest to the sun. Similarly, max would be L square by K mu divided by 1 minus epsilon, right? That would be your aphelion, right? And that occurs, this was at theta is equal to 0. This is when theta is equal to 180 degree or pi, right? So this will be your A. Okay. And then we calculated, uh, so this was mostly formulas, right? Deriving formulas. So epsilon was in terms of energy and angular momentum was this one divided by mu k square. So if you give me energy and angular momentum, I'll tell you what epsilon is, and therefore what kind of orbit you have, right? And then you can calculate A, that is the semi-major axis, which turns out to be minus k over 2e, which is evidently independent of L, angular momentum, but you can have energy set as a function of L also. So if the energy is given, then it's independent of L, right? And once you know A and epsilon, B is just A times square root of 1 minus epsilon square. So this, out of these three, two are independent. If you give two of this, I can calculate the third one, right? Okay. So in terms of A, that is the semi-major axis, we can write R as A into 1 minus epsilon square divided by 1 plus epsilon cos theta, right? And then we finally wrote the third law of Kepler, which was T square is proportional to AQ. This he firstly derived from the observations, particularly the observations done by another physicist named Tycho Brahe, right? So he just put in the numbers and plotted. I don't know exactly how he did it, but at the end he found empirically that t square is proportional to a cube. And of course, then Newton comes and gives the theory, and then he immediately sees that this has to be the case, right? And so t is proportional to a to the power 3 by 2. And if you write the constant, it turns out to be 2 pi a to the power 3 by 2 square root of mu over k. Okay, so where a is the semi-major axis, right? So now if you have trajectories of two planets, let's say just the phase plot for Earth and Jupiter, and you want to compare the time periods, now you can do that. If Jupiter is twice as far, then the time period is not twice or four times. It will be 2 to the power 3 by 2 times the time period of the Earth. Okay, so this way we can calculate the time periods for different planets or different orbits in general. There was another thing that we learned, and this was something new. The other things you might have learned in class 11th or 12th as well, at least the primary facts. But we discovered a vector called Laplace-Runge length vector, and that is given by P cross L minus mu k r cap, right? And then it turned out to be mu k epsilon times rp cap, where rp cap is just your vector from your focus or sun to perihelion, right? So no matter, even if you are here, your vector A is same thing. It's it always points towards the perihelion, in the direction in which focus is towards the perihelion. So in this case, A would be uh, constant both magnitude wise and direction wise. So dA by dt is 0. Okay. And then there was last class when we talked about solid or rigid body, right? Most of that lecture was spent in philosophical meaning of what particle is and what rigid body is. And the conclusion was that when we either don't know the internal structure of something, or the scale is such that the internal structure is irrelevant, then we consider it to be a particle. And once you have defined your particle that way, for example, if you are uh, doing something on scale of universe, then the galaxies could be particles. On scale of solar system, the planets could be considered as particles, right? But if you are doing some nanoscience, then the atoms, not even atoms, even the electrons have to be considered as particles, right? So the definition changes according to the size of the given problem. And this is kind of the essence of physics, that you define your things, you exactly know what you should consider and what you shouldn't consider, right? And this is something that separates physics from mathematics, in my opinion. So rigid body would be something that is a collection of particles, and the distances between them are just fixed. A, B, C, D. They don't change, right? None of them. And then we argued that degree of freedom for a rigid body is 6. And this 6 turns out because you have 3 translation degrees of freedom for any one particle or say center of mass, and then uh, choose an axis for which you have 2 degrees of freedom, any polar angle or azimuthal angle, right? And then you can rotate around that axis by any angle. So it's 3 plus 2 plus 1, which is 6, right? So one way to imagine is that consider yourself as a rigid body. You can first do some translation, that is 3 degrees of freedom. and then define an axis through your hand, and that hand can point in any direction. So those are 2 degrees of freedom, and then your hand can move along this direction. So that is one more degree of freedom. And if it is pivoted, then you no longer have this 3 translation degrees of freedom. Then it just becomes 3, right? So that's all we learned this week. And then any questions? If not, then let's proceed to the questions. So from the previous year, I had access to 2 questions. The first one is an attractive potential 1 by r. Compare circular and parabolic orbits corresponding to same angular momentum. Okay, so you have a circular orbit with same L, and you have a parabolic orbit with same L. And what is given is that perihelion distance of the parabola, which is this distance, right? E is alpha times the radius of the circle, alpha times the radius of the circle. So this is r, and it's given that E is alpha times r, and we have to find what is alpha. Okay. The only piece given is that in both the case angular momentum are same. So how do you proceed? How do you solve? First step is to find the right formula for it, and in this case it is just the general formula which we saw, that L square over K mu divided by 1 plus epsilon cos theta, right? So for circular we have epsilon is equal to 0, which means r is L square over Kb, right? Constant, as it should be, and this is your radius r. Great. For parabola we have epsilon exactly equal to 1, which means r is L square by K mu over 1 plus cosine theta. Now what is perihelion? Perihelion is the minimum distance to the sun, right? In the orbit, as you come closer, then go on. So at this point you are closest, even though in figure it may not seem like this because I just wrote. But in this it's very clear that to have the minimum value, what you have to do is the numerator is constant, so denominator should be the least one, and which means cosine of theta should be highest, which is 1. So it becomes 1 plus 1. And when is cosine theta is equal to 1? Is when theta is equal to 0. Right? So that is when the distance becomes the minimum, and it is 1 plus 1. So L square by 2k mu, right? Which is just r by 2. Right? This was our r. This means T is 1 by 2 r, which means our alpha is this thing. So the correct answer is 1 by 2. Clear? Okay. So to the second question. Okay, before we do the second question, there is another part of this question which is not there in the assignment. But anyways, it's interesting. So I thought maybe we can do it. And it is that prove that in the same central force as in part 1, the speed of particle at any point in a parabolic orbit is square root of 2 times the speed in a circular orbit passing through the same point. Okay, so now we know we have circular orbit, right? And there is parabolic orbit. right? And what it says is that velocity of parabolic orbit is square root of 2 times velocity of circular orbit. And how do you solve it? Can anyone guess how should you tackle it? Oh, there are some messages. Shouldn't epsilon be less than 1 for E less than 0? Oh yeah, did I write it wrong?
I think you corrected it afterwards. It
Oh, okay.
was initially wrote as epsilon less than 0.
Yeah,
So
yeah,
that's
yeah.
what it is.
My bad. Epsilon and energy are always I get confused with. Okay, okay. I'll proceed. Right. So the argument is that uh, energy, let's say for circular path, cir- circular orbit, your energy is the minimum energy, right? Which was we wrote it this one, half mu k square over L square minus half mu k square over L square. And we also know radius in terms of this, which was L square over mu k. Let me just confirm. Yeah, it's L square over mu k, right? So the energy becomes minus half k, and this thing is just r, right? So this L square over mu k is r. So okay, for circular orbit, the energy is this one. What about parabolical orbit? Energy is by definition 0, right? It means half of mv p square minus k by r is equal to 0, which means half mv p square is equal to k by r. And for this case, we have half mv square vc square minus k over r. This is your total energy, and that is equal to minus 1 by 2 k over r. Okay, and once again, so Vp is equal to square root of 2k by m r, right? And for this case, okay, I'm using two different r's, but you know it says r is small r and capital R same because we have only one r, right? Again, I did the mistake. Okay, so because we have r is equal to capital R, it's circular orbit. So half mvc square would become k by r minus half k by r. So again k by 2r. So vc would become, these 2's get cancelled, square root of k by mr, right? So now this vp can be written as square root of 2 times the same thing here and here. So it is vp square root of 2 times vc, which is exactly what we wanted to show. Okay, it's just the same. Yeah, Okay. So one more question from assignment. By the way, that was clear, right? Straightforward. Not conceptually very difficult. It's just that algebra could be sometimes involved. Okay. Another question. Again, same flavor. Use the equations. Use the right equations, and you will be able to do that. So now this question is. Let me zoom in a little bit. A rock is thrown vertically upwards from the surface of Earth. It reaches a maximum distance of alpha r from the center. Here r is the radius of the Earth. Okay, so this is your Earth, and the rock is thrown with some velocity v, and it reaches a maximum height, which is alpha times r. Okay, this is the radius of Earth. Okay, v denotes the velocity of rock when it was fired. Now imagine that same rock is taken to a distance beta r from the center of Earth. Okay, so now instead of firing from the surface itself, it's fired from some distance beta r. Okay, and then fired with the same speed v as before, but this time the direction of v is not along the line joining the stone and the center of Earth. The path of the stone will be parabolic if so. Now it's thrown with the same speed v, but not along this direction, joining the location of the stone and the center of the Earth. And the question is, if this follows a parabolic path, then which of the following is true? So we have to calculate 1 by alpha plus 1 by beta, right? The information we are given is that this path is parabola, which means its energy is 0. Okay, so first let's calculate this case. So we have case 1 and case 2. For case 1, the initial energy is half mv square minus k by r, right? That's where it's fired. So this is your EI, and EF is when it just reaches there is no velocity. So it's just minus k over alpha r. This is 11th standard physics. So we equate both of this because the energy is conserved. This is equal to minus k by alpha over r, which means half mv square is k over r 1 minus 1 by alpha. Okay. In the second case, it's thrown from a height beta r, right? So now EI is 1 by 2 mv square minus k upon not r but beta r, right? And what should this be equal to, given that the path is parabolic? What would be its energy?
0.
0,
That would
right?
be 0.
Right. So that's what is given. This is equal to 0 because parabola. But we know half mv square because we are given that the speeds are same. So half mv square is k by r into 1 minus 1 by alpha, and this is minus k by r 1 over beta, right? Now I can cancel out this k over r. What we are left with is 1 minus 1 by alpha minus 1 over beta is equal to 0. That's same as saying 1 by alpha plus 1 by beta is equal to 1. Okay, I don't know how to make physical sense out of it. I, I think it's just an exercise in algebra. nevertheless the correct answer is 1. Okay, anyways, we can think of one case: what happens when alpha is equal to beta and both of them should be equal to 2, because 1 by 2 plus 1 by 2 would be 1, right? That means if your particle just reaches the height equal to 2r, so height is just hr, then if you throw it from the same height, it will go to parabola, right? So if you throw a stone and it goes somewhere, and mark that point and start the trajectory from that point with the same velocity, and it will go to parabola, right? Okay, and there was one more question. I messed up the order, never mind. The question is, we have two particles moving about each other in circular orbits under influence of gravitational forces, and the time period is t. Their motion is suddenly stopped at a given instant of time. So now they are stopped. So they will start attracting each other. So they are released and allowed to fall into each other. Prove that the time it takes to collide is t over 4 square root of 2. Okay. So before, we can think of in center of mass coordinate. So you have r, and it was doing this circular orbit thing with some time period t. At some instant, both were stopped, right? So they started pulling each other. So in circle center of mass frame, we have this r, and this particle will just keep on coming closer and closer, and at the end r would be equal to 0, where both of them just collide, right? And we have to uh, calculate what time it takes, so call it t prime, right? Okay. So first thing, this is 1 and 2. For 1, we already know it's just a Kepler's problem, right? With A is equal to R. So let's say this radius is R, then T is 2 pi A to the power 3 by 2 square root of mu by K. This is just Kepler's third law. Let me add a page. Now second is slightly trickier. Now we have different questions, but that there are two particles, they are separated by distance a, right? And how long does it take to fall into each other? So the force on this is minus gmm by r square, or minus k by r square, right? So the equation is just d2r by dt2 is equal to minus k over r, right? And we have to solve this. So at t is equal to 0, we have r is equal to a. This is our boundary condition. And at t is equal to t prime, which we have to find, r is equal to 0. For this, first we note that energy is conserved, which means we can write half m v0 square minus k over initial separation, which was a, is equal to, at any other time, we have half mv square, where v is a function of time, minus k over r, where r is also a function of time, right? So v is v of t and r is r of t at any given time. So, and we know that v0 is equal to 0 because they were stopped and then released, right? So v0 is equal to 0. So the equation becomes half mv square. I'm writing right hand side and send this to the left hand side. K over r minus k over a. So we get v is equal to square root of 2 2k over m. Sorry, I shouldn't use m, right? Mu. 2k over mu 1 over r minus 1 over a square root. Okay. And v is dr over dt. So square root of 2k by mu square root of 1 by r minus 1 by a. This is now solvable because we have two variables r and t. So let's separate them. Dr upon square root of 2k over mu and square root of 1 by r minus 1 by a is equal to dt. And then let me add a page. Then we have to integrate, and the integral for time is 0 to t prime, and for r it is a to 0. Yeah, one more thing. For this equation we should have minus sign because we know that dr by dt is negative. They are coming together, so r is decreasing as a function of time, right? So there is negative here, so there will be negative here. Okay, so now I can pull out this factor mu by 2k, right? Right, and then from 0 to a, so I'm observing this negative sign and switching the limits, and then dr over square root of a minus r, and on the numerator we have square root of ra is equal to just t prime. So we have to evaluate this equation, this integral. So I can take out square root of a as well, but then at the end we realize that in the denominator we have this quantity square root of a minus r. So sensible substitution would be r is equal to a into sine theta, right? uh, Sine square theta, which means this denominator would become square root of a minus a sine square theta. So square root of a into square root of 1 minus sine square theta. So square root of a into cos theta. So just to make the denominator nice, we are doing this transformation. Okay. So how would dr look like in theta? So a into derivative of sine square theta, which is 2 sine theta cos theta times d theta. So now the integral would look like 0 to a. Now when r is equal to a, it means sine square theta is equal to 1, which means theta is equal to pi by 2. So we are going from 0 to pi by 2, and dr is 2a sine theta cos theta d theta, and then square root of r, which is square root of a into sine theta, and again square root of a, right? And denominator we have this thing square root of a cos theta. Okay, and now many terms get cancelled. Cos theta square root of a square root of a. So and these factors are constant, so we have 2a root a square root of mu divided by 2k integral of sine square theta d theta from 0 to pi by 2, right? This is some integral which has some constant value. Can anyone tell me what is the value? Yeah, it's pi by 4, and we'll show it. But if it is pi by 4, let's just believe that is true, then this entire thing is 2a root a into pi by 4 square root of mu by 2k. So pi divided by 2 root 2 square root of mu a cube divided by 2k, right? This is your t prime, and what was your t? T was 2 pi times the factor, so it's 2 pi times square root of mu a cube by k. Sorry, there is no 2 here. Okay, so t prime divided by t, which is what we want to find, be 1 by 2 root 2 divided by 2, and all other factors get cancelled, right? Pi and square root of mu a cube by k, which is 1 by 4 root 2. So we have t prime is equal to 1 by 4 root 2 t. Okay, that's what we wanted to find. This time is t divided by square root of 4 root 2. Sorry, 4 times square root 2. But we missed one step, which was evaluating this integral. So I was 0 to pi by 2 sine square theta d theta. Now there are two ways to solve that. That's why I kept it at the end. The first method is, if you have integral from a to b f of x dx, it's same as evaluating from a to b plus a, no, a to b, and this should be a plus b minus x dx, right? So instead of x you can have a plus b minus x. So same way, I is 0 to pi by 2 sine square theta d theta, which is same as 0 to pi by 2, and instead of sine square theta I can have pi by 2 minus theta, because a plus b is pi by 2. So pi by 2 minus theta d theta, this is 0 to pi by 2 cosine square theta, right? Sine pi by 2 minus theta is cos theta. So I is this also. So if we add both of them, let's say this is 1, this is 2, then we have I plus I is equal to integral from pi by 2 sine square theta plus cos square theta d theta. So 2I is equal to 0 to pi by 2, this is 1 d theta. So this is just pi by 2, which means I is pi over 4, right? So this is a standard method. Another method which is direct, not as elegant though, is again I is 0 to pi by 2 sine square theta d theta. So we know that cos 2 theta is 1 minus 2 sine square theta. So sine square theta would be, take 1 that side, 1 minus cos 2 theta upon 2, right? So I can write sine square theta as 1 minus cos sine of 2 theta upon 2 d theta. So I can break it down into two integrals, 0 to pi by 2 1 by 2 d theta minus 0 to pi by 2 cos 2 theta with half, right? This one is just pi by 4, pi by 2 times half, right? And minus, for this integral of cosine 2 theta would be sine 2 theta divided by 2, right? And with boundaries 0 and pi by 2. So for at pi by 2, sine 2 theta is sine pi, which is 0, and at 0, obviously it's sine 0, which is 0. So both the boundaries are equal to 0. So this is 0, and I is again pi by 4. Okay. Once you had the I, we got the result. Okay. So those were the questions I wanted to solve. If you have any questions now, please ask. Okay. Meghnad, Amar, do you have any questions? Meenakshi ji? Okay, I'm guessing not. Okay, no. Okay, then let's stop here. I think we had only few lectures this week, so it's only appropriate that we had only few problems. And nevertheless, these problems are conceptually easy. It's just that when you do the algebra, it takes some time. So the only way to get used to this is by doing it by yourself. So try to do as many problems as you can, and that's the only way to get used to this. Okay, so with that, we'll end the discussion here. We'll meet next week, same time. Bye bye.